Episode 10, Unit 3, Wind Energy. In this episode 10, we will discuss about forces on the blade. We already discussed what is power coefficient. Cp is equal to power output from wind machine divided by power available in wind. Here blades of propeller type wind turbine is considered. There are two types of forces which are acting on the blade. One is circumferential force acting in the direction of wheel rotating that provides the torque, and other is the axial force acting in the direction of the wind stream that provides an axial thrust that must be counteracted by proper mechanical design. The circumferential force or torque capital T can be obtained from capital T equal to P divided by omega. P divided by omega is equal to pi capital D N. Here capital T torque, kilogram or Newton. Omega angular velocity of turbine wheel meter per second. D is diameter of the turbine. Capital N is wheel revolution per unit time, second inverse. The real efficiency eta is equal to capital P divided by P total. P total is equal to eta into 1 by 2 Gc rho AVI cube. Then the equation is equal to eta into 1 by 2 Gc into rho pi divided by 4 into d square Vi square divided by pi dn. That is also equal to eta 1 by 8 Gc into rho dvi cube divided by n. At maximum efficiency, n, that means eta max, is equal to 16 divided by 27. The torque has maximum value T max, which is equal to 2 divided by 27 GE into rho capital D Vi cube divided by n. The axial force on a turbine wheel operating at maximum efficiency, where Vc is equal to 1 by 3 Va, is given by Fx max equal to 4 divided by 9 Gc rho A Vi square is also equal to pi 9 Gc rho d square Vi square. We see that the axial force are proportional to the square of the diameter of the turbine wheel. This limits turbine wheel diameter of large size. Next we move on to wind energy conversion. Traditional windmills were used extensively in Middle Ages to mill grain and lift water for land drainage and watering cattle. Wind energy converters are still used for this purpose today in some parts of the world, but the main focus and attention now lies with the use to generate electricity. There is also growing interest in generation heat from the wind for space and water heating and for glass houses, but the potential market is much smaller than for electricity generation. The term windmill is still widely used to describe wind energy conversion system. However, it is hardly an apt description anymore. Modern wind energy conversion system are more correctly referred to as WECS, aerogenerators, wind turbine generator, or simply wind turbine. The fact that the wind is variable and important source of energy is immaterial for some applications such as pumping water for land drainage provided. Of course, that there is a broad match between the energy supplied over any critical period and the energy required. If the wind blows, the job gets done. If it does not, the job waits. However, for many of the users to which electricity is put, the interruption of supply may be highly inconvenient. Operators or users of wind turbine must ensure that there is some form of backup to cover period when there is insufficient or too much wind available. For small producer, backup can take the form of battery storage, connection with local electricity distribution system, a standby generator powered by liquid or gaseous fuel. For utilities responsible for public supply, the integration of medium size and large wind turbines into their distribution network could require some additional plant which is capable for responding quickly to meet fluctuating demand. Small producers, that means private citizens in several countries, have won the right to operate wind generators and other renewable energy systems to export power to the grid. For most small wind generator, this requires that the output is conditioned so that it conforms to the frequency and phase of the main supply. Only a few small units are designed to maintain a constant rotational rate so that can be synchronized to the mains frequency and feed electricity directly into the grid. Most produce direct current DC or variable output alternating current AC. Power conditioning is readily achieved using an electronic black box called synchronous inverter, and although this is an expensive item of equipment, it does not eliminate the need for batteries and for conversion of home appliances to turn and run on DC. Where there is no grid connection, electricity that is surplus to immediate requirements must be stored on site using heavy duty batteries. It can be recovered later when the demand exceeds the supply. An alternative is dump it, that means by generating and dissipating heat, or better to convert into heat that can be stored, for example as hot water in a well insulated tank. Then move on to large producer. Large and medium sized wind generator are designed to give a stable and constant electrical output over wide range of wind speed and to feed current directly into the grid. They operate primarily as fuel savers, reducing the utility total fuel burn. The choice of generator type depends on the size of the local distribution grid and its associated generating capacity. An induction generator would normally be used where there is significant amount another generating capacity, which could provide the necessary reactive lower for excitation. Induction generators are reliable and require minimal control equipment. For isolated networks where other local generating capacity is limited and where a high degree of autonomous control is required, a synchronous generator is more appropriate. Synchronous generators are more complex and therefore more expensive than induction machines. The basis for wind energy conversion: lift and drag. The extraction of power and hence energy from the wind depends on creating certain force and applying them to rotate or to translate a mechanism. There are two primary mechanisms for producing forces from the wind. Lift and drag. By definition, lift force act perpendicular to the airflow, while drag force act in direction of flow. Lift force are produced by changing the velocity of the airstream flowing over either side of the lifting surface. Speeding up the airflow causes the pressure to drop, while slowing the airstream down leads to increase in pressure. While slowing the airstream down leads to increasing in the pressure. Any change in velocity generates a pressure difference across the lifting surface. The pressure difference produces a force that begins to act on high pressure side and move towards the low pressure side of lifting surface, which is called an airfoil. A good airfoil has a high lift-drag ratio. In some cases, it can generate lift force perpendicular to the airstream direction that are 30 times as great as the drag force parallel to flow. The lift increases as the angle formed at the junction of the airfoil and airstream, that means the angle of attack, becomes less accurate up to the point where the angle of the airflow on the low pressure side becomes excessive. When this happens, the airflow breaks away from the lower pressure side. A lot of turbulence ensues. The lift decreases and drag increases quite substantially. This phenomenon is known as stalling. For efficient operation, a wind turbine blade needs to function with as much lift and a little drag as possible because of drag dissipated energy. As lift does not involve anything more complex than deflecting the airflow, it is usually an efficient process. The design of each wind turbine specifies the angle at which the airfoil should be set to achieve the maximum lift to drag ratio. In addition to airfoils, there are two other mechanisms for creating lift. One is the so-called Magnus effect, caused by spinning a cylinder in an airstream at high speed of rotating. The spinning slows down the airspeed on the side where the cylinder is moving into wind and increase it on the other side. The result is similar to an airfoil. This principle has been put to practical use in one or two cases but is not generally employed. The second way is to blow air through narrow slots in a cylinder so that it emerges tangentially. This is known as WECS slots. This is also creates rotation or circulation of the airflow, which is turn generates lift. Because the lift-drag ratio of airfoil is generally much better than those of rotating or slotted cylinders, the latter techniques probably have little practical potential. The very important symbols in the blades, capital V is free wind velocity, capital V suffix B velocity of airfoil element, capital V suffix small r resultant wind as seen by airfoil element, capital F base L lift force, that means perpendicular to VR, capital F suffix D drag force, theta is angle of twist, alpha is angle of incident, omega is angular of speed of rotator, small r is distance of airfoil element from its axis of rotating. The windmill blade sees the resultant vector VR. The blade need to be twisted because small r varies in proportion to radius. Wind at 1 standard atmospheric pressure and 50 degrees Celsius has velocity of 50 meter per second. Calculate the total power of density in the wind stream, the maximum obtainable power density, a reasonably obtainable power density, the total power, and the torque and axial thrust. Turbine diameter is equal to 120 meter and turbine operating speed is equal to 40 rpm at maximum efficiency. Propeller type wind turbine is considered. Then we can solve this problem by using the equation rho is equal to capital P divided by RT, and also we can use the power density formula P total divided by capital A, and also we can use maximum power density formula P max divided by capital A. Then we can use total power capital P formula, that means power density and area. Finally, we can find T max and Fx max. The answer for the Fx max is 1385,870 Newton. This is the right answer. The wind velocity at a given height can be represented in terms of gradient height and velocity. That means B divided by Vg suffix is equal to H divided by Hg suffix whole power small n. The value of Vg, Vh, Hg and small n depends on the nature of the terrain, which are classified as open terrain with few obstacles, that means open land, lake, shores, deserts, etc. Terrain with uniformly covered obstacles, woodlands, small towns, suburbs, etc. Terrain with large and irregular objects, that means large city centers, country with breaks of large trees, etc. In as much as the height of the windmill rotate depends on the design wind velocity and cost of supporting structure. The above factors have bear on the design. Similarly, winds being unsteady phenomena, the scale of period considered for these temporal parameters such as scale of hour, month, year is an important set of data required in the design, while the hourly mean velocity, that means for many years, provides the data for establishing the potential of the place for tapping the wind energy. The scale of the month is useful to indicate whether it is going to be useful during particular periods of year, and water storage, if necessary, is to provided for as already mentioned above. The data based on scale of the hour is useful for mechanical aspects of design. In addition to the data and the hourly mean velocity, two other information required are spells of low wind speed and gusts. The former again for providing storage or alternative, the latter is required for structural design of windmill as well as to provide safety measurement against damage. A number of criteria can be applied in estimating the importance of wind potential as a function of height and location. First of all, careful sighting is important because wind speed near the ground is greatly affected by houses, trees, and similar features as stated above. Wind speed increases with height above ground if rate of increases being about the same at all locations. Therefore, if the wind speed at a given height is known, the speed at any other height may be calculated. Surface wind data on a national or regional basis is usually presented in the form of isovan or contours of constant average wind velocity meter per second or kilometer per hour. The averaging period seen in the literature varies widely, but monthly, quarterly, and yearly averages are commonly seen. It is important to know what the data averaging period is when examining a given isovans and contour map. For the winds change seasonally, it is seen that only some parts of the country have reasonably good velocity. Even at the other zone marked with low wind velocity, one can always find spots high winds depending on the topography. Wind surveys. Typical wind measurement at potential sites for wind machines usually require the following: instrumentation, 3-cup anemometer and wind direction sensors. Height of instruments 10 meter, that means 30 feet for preliminary data, 15 meter to 45 meter, that means 50 to 150 feet for long time data. Data recording system: strip chart, magnetic tape, type of data, wind speed and directional Hawley average, data reporting, wind frequency curve, daily, weekly, monthly. The energy estimation. The basic wind data of Hawley mean wind velocity is recast into number of hours in the year for which the speed equals and exceeds each particular value. Annual hour of duration of various wind speed. The first of these plotted amongst the hour in the year is called the velocity duration curve. The replot of this on VQ basis called the power duration curve, VQ being proportional to P. These curves are useful for establishing the wind energy potential of a place and the design wind speed. The plot of the second form of data of number of hours for which mean wind velocity of a particular value is available is called the frequency duration curve. This curve is useful to deciding the design wind speed for a given site. Once the type of windmill is decided and its performance is known, the data is also useful estimating the actual energy output the plant. The 3 speed associated with the design of a windmill or VC is cut in speed, the speed below which the windmill does not operate. VD is design speed, the speed of which the rotator is designed. VF is furling speed, the speed at which the rotator is turned away from facing the wind or stopped otherwise with a view to protect the windmill. All these speeds have a bearing on the mean wind velocity of the place. Another reference speed is rated V rate, at which the plant output is maximum. The 3 speeds are marked and A, B, C, D is represented the annual energy output from an ideal plant. The area A, B, C, D represents the output obtainable from the ideal plant if the windmill were operate at the design speed all the time. The ratio of the area and annual loaded factor of the plant is very interesting one. Thank you.